In the determination of a weak acid dissociation constant lab, the fifth solution that you're going to be testing and using to determine a value for Ka is actually one derived from a titration. The titration shown here at left consists of the pH probe immersed in a solution that contains 15 milliliters of 1.0 molar acetic acid, along with an additional 15 milliliters of distilled water. The reason for the additional 15 milliliters of distilled water is to bring the level of the solution up to a point where the pH probe has been properly covered. Also notice the beaker is positioned on a stir plate. You have a stir bar. I would recommend stirring between 500 and 600 RPMs just to keep the solution mixing as quickly as possible, and of course no heat is used in this experiment. We're going to be titrating this weak acid, acetic acid, with 1.00 molar sodium hydroxide, a strong base. And we're going to be doing that titration in increments of 0.40 milliliters. You'll be adding slowly the sodium hydroxide, and it will be mixed with and neutralize the acetic acid we have in the container down below. Now, along the way, you will be manually constructing a data table that you'll be using later in an Excel spreadsheet to create a titration curve, which we'll cover in just a moment. Take your initial reading when the burette reads 0.00 milliliters and write down the pH. Then add 0.4 milliliter, record the pH again after it has settled down. Wait no more than 10 to 15 seconds. Some drift is always occurring with these rather inexpensive pH probes. Then again add another 0.4 milliliters to bring the total up to 0.8, record the pH, and so on. Okay, we're going to be stopping once the pH has reached its maximum value, and just to give you a peek of things to come, we would like at least 6 data points up on the highest pH plateau, just to make sure that we have a good picture for the titration curve. Once you've collected all of the data, you're going to be plotting that data in a graph known as a titration curve, which is the pH that you measure versus milliliters of sodium hydroxide on the x-axis. Now I'm going to sketch out a very crude titration curve just to show you how that might look. Being an acid, acetic acid begins with a rather low pH, and as you add your sodium hydroxide, the pH is going to always increase. After all, you're adding something that has a very high pH. Sodium hydroxide is a very basic solution, and adding any amount of sodium hydroxide can have no other effect than to increase the pH. And so as we continue to add the sodium hydroxide, we enter into a region where the pH doesn't seem to be changing very much, but note that it is still increasing. We will reach a point, however, where the pH will dramatically increase before it finally levels out, increasing only in very small amounts. Notice that up here we have about 6 data points, and that's what we hope to have once everything is over with. And so make sure that you get enough data points up there on that final plateau to properly complete this curve. Now, the various parts of this titration curve are really very important. The first point that I'm going to point out to you is the equivalence point. Now, to determine the equivalence point, what you need to do is you need to establish about as high as the pH goes and about as low as the pH goes in this region and decide where the halfway point would be. And so we're trying to identify where halfway would be between these 2 points. Now, I'd like you to notice that currently there is no data point in that midsection, and that's where it's going to require from you a little bit of approximation, okay? And so as you think about this curve and how these data points are connected, you can see that on the steep slope, we have such a steep slope that we don't have a data point at its midsection, and I'm going to eyeball that and approximate this point right here as the equivalence point. Okay. Now, the equivalence point is that point where the number of moles of sodium hydroxide equals the number of moles of acetic acid. This is the point that, and I'm sure you have, whenever you've done an acid-base neutralization reaction, this is the one point that you're hoping to accurately identify, because you can use this point to accurately determine the concentrations of either the acid or the base, depending upon what happens to be missing. And the way you would do that is, knowing where the equivalence point is, you would draw a line down to where it meets the x-axis, and at that point then you would have the milliliters of NaOH required to get to the equivalence point. And if you know the concentration, as we do, of sodium hydroxide, you can also, from these two values now, get the number of moles of sodium hydroxide that were used. And the number of moles of sodium hydroxide used, because it's a 1-to-1 stoichiometric ratio, is equal to the number of moles of acetic acid. And so we can learn something about the acetic acid from this point. Now, in past titrations, you didn't have a pH probe to show you where the equivalence point was. Rather, you had some sort of colorful indicator. And an indicator is a liquid added to the lower beaker that changes color at a pH appropriate for this particular equivalence point. So as I look at this equivalence point, its pH can be identified as being in the vicinity of 9. And so we would want to choose a colorful indicator whose color change occurred as close to 9 as possible. We wouldn't want the color change to occur at, say, a pH of 4 or 5, because that pH would occur much too quickly, way before the equivalence point. And similarly, you wouldn't want an indicator that changed color in the vicinity of pHs 11 and 12, because that would be too late. So we pick a colorful indicator to change in the vicinity of the equivalence point, and we fortunately in this experiment get to see the equivalence point by virtue of this pH measurement that we're making. Okay, so just to wrap that up, approximate the position of the equivalence point. That point will probably not coincide with a data point that you've already measured. Rather, you're going to be approximating it, and then you're able to identify the milliliters of NaOH as well as the pH at that equivalence point. Now, the next part of the graph is quite important, and that is this point, or this region in this area right here. This is known as the buffering region. And the buffering region is a region where the pH changes slightly. Okay, as I mentioned earlier, the pH is always increasing, but in this buffering region, the pH is only increasing by small amounts. So this buffering region is something that we'll have to approximately get, and then from the buffering region, we're able to get some very useful information, namely the pKa point. Now, what we're going to do next is we're going to look at this buffering region and attempt to decide, now we're working horizontally, attempt to decide where the halfway point is in the buffering region. That is, where are we right in the middle of the buffering region? This is going to be something of an approximation. I don't have a ruler that I could use, but I'm going to just use the best that I can and approximate that point as the midway point in the buffering region. Just as was the case for the equivalence point, there may not be a data point that coincides to the point you choose as this particular point. And speaking of this point, this is called the pKa point. Okay? And the pKa point is that point where the number of moles of acetic acid, CH3, COOH, is equal to the number of moles of acetate ion, CH3COO minus. You see, initially, at the beginning of this titration, what we had mostly was acetic acid. with only small amounts of acetate present in order to maintain the equilibrium. However, as the sodium hydroxide reacts with the acetic acid is converted into acetate ions. And when we reach a point where we've used up half of the acetic acid and converted it into an equivalent amount of acetate ions, we've reached the pKa point, which is also called, not coincidentally, the half equivalence point. Because in theory, we've reached a point now where half of the acetic acid has been neutralized and converted into acetate ions. All right. Now, what we can get from this point, and I'll refer to it now as the pKa point, is a value for the pKa. We take that point and we extend a line over to see where on the y-axis we are. This point right here is called the pKa point. And after you've identified your pKa point, it's important that you determine a value for pKa from your graph. So the graph is really being used in this sense to determine a value of pKa. And what is pKa, you might think? Well, let's go back to some fundamental definitions. We know that the pH of a solution is equal to the negative log of the hydronium ion concentration. We also know that the pOH of a solution is equal to the negative log of the hydroxide ion concentration. You can probably see a theme developing here. The idea is that we're using logarithms to more easily describe numbers like hydronium ion concentration and hydroxide ion concentration that vary over many, many orders of magnitude. In a similar way, we can also say that the pKa is equal to the negative log of the Ka value. And from this definition, with a little bit of algebra, we can actually determine a value for K sub A. K sub A will be equal to 10 to the negative pKa. All right, so having done that, what you can now do is, from your graph, determine a value of pKa, plug the value of pKa that you got from the graph into this expression, and determine a value for the weak acid dissociation constant for acetic acid. And then, of course, you'll be comparing this value of K sub A to the known value, as well as to the previous 4 values you determined via simple pH measurements.